All right, so even though we can find this inverse transform by using partial fractions, let's illustrate the use of the convolution theorem to find this inverse. So remember that the Laplace transform of a convolution is the product of the individual transforms. So that's the idea we're going to use. So obviously the convolution theorem is kind of limited when finding inverses. We have to be able to write our transform as a product of two other transforms. So the thing to notice here is that 1 over s times s squared plus 9 is 1 over s times 1 over s squared plus 9, which are actually two individual transforms. This is the transform of 1, and this is the transform of, well, let's see. Normally when there's a constant upstairs, we're expecting a 3 for this one since a squared is 9. So this is 1/3 sine of 3t. So now it's time to set up the convolution integral to get back to the original function. So looking at this, I want to choose f of t, or f of w rather, to be the simpler one. Well, f of w is going to be the simpler one. G of t minus w is going to be the more complicated one. So I would say use this one as f, because you don't want to have to substitute a t minus w in there. And I would say this is g, because if you plug in t minus w to that, you still get 1. So that means that we have the integral of 1/3 sine 3w times 1 dw, all from 0 to t. So we're just a step away from finding the inverse transform. So let's see how this integrates. So antiderivative of 1/3 sine 3w is negative 1/9 cosine 3w, evaluated at t and 0. And that looks like negative 1/9 cosine of 3t minus negative is plus. 1/9 cosine is 0 is 1/9. And there it is. I'll just write it as a 1/9 out front, 1 minus cosine 3t. And there we have it. That is the inverse by convolution theorem. Thanks for watching.